Good morning, students. I hope you all are well and doing mathematics comfortably. Till date, we have done vector space, vector subspace, linear combination, span, spanning set, and a particular theorem. Today, we extend the structure of vector space by defining some more terms. So, let us see. As you know that if V1, V2, V3 belongs to V, vector space such that then this is theorem, and in the last video we have proved it. Span S is a subspace of V. And what is span S? It is nothing, a set of linear combinations of all these vectors. Again, equals to V. That means if each vector of V is linear combination of, then S is called spanning set or generating set. If a span of this is V, that means if each vector of V is a linear combination of all these. Now listen, let this is a set having three members 1 0 0 1 2 minus 3, and here is a subset of R square, and R square is a vector space. You people know that. V equals R square, that is x comma y, such that x y belongs to R. So these are the members of this R square, and this particular set has three members, that is 1 0 0 1 2 comma minus 3. Here you see 2 comma minus 3 is 2 comma minus 3 is 2 times 1 comma 0 and minus 3 times 0 comma 1. That means one of the vectors of S is linear combination of others. See the observation. This is the subset of R square. These are the members of R square, you can say. So 2 comma minus 3 is written 2 times of 1 comma 0 plus minus 3 times of 0 comma 1. So you say this is a linear combination of 1 comma 0 and 0 comma 1. Means one of the members is linear combinations of others. Here you can see. If we have this type of situation, then the set S is known as linearly dependent. What is the name? Linearly dependent. So, how to define? Let a set of vectors of the vectors let a set of vectors, this one, of the vector space V is such that at least one of the vectors is a linear combination of others, then the set of vectors is called linearly dependent. Okay, let us revise. These are the vectors of the vector space V, and these vectors, that means these are the members of V, is such that at least one of the vectors is a linear combination of others, then the set of vectors is called linearly dependent. If it is not linearly dependent, then we say independent. Okay, so for this example, in R square, the set is linearly dependent because 2 comma minus 3 is or you can write, suppose I write 1 comma 0, then this is 1 times 1 comma 0 plus 0 times 2 comma minus 3. You can say this. Or you can write at least one of them is linear combination of others. Here this is also written in terms of this one, this is also written in terms of this one, also written in terms of. So if we have n vectors, if any one of them, at least one, not all, at least one, suppose I say V3 is a linear combination of others, then this set is known as linearly dependent. Okay. See some other examples also. Let F be the set of real valued functions defined on number line, that is minus infinity to infinity. Let V1 is sin x, V2 is cos x, cos square, sin square, and V3 is cos 2x. Definitely here sin square x, cos square x, cos 2x, these are the members of F. And here you remember this is a vector space, but cos 2x is rewritten as cos square x minus sin square x. You people know the formula, or you can write 1 times cos square x sin square x. So here cos 2x is linear combination of cos square x and sin square x. Now remember, cos 2x is written as cos square x minus sin square x, and this is a linear combination of this one. Therefore, the set V1, V2, V3, this is right, sin square x, cos square x, cos 2x is linearly dependent. Okay. So the alternative definition. A set of vectors of the vector space V there are scalars such that at least one of them is non-zero. A set of vectors of the vector space V, there are scalars C1 to Cn such that at least one of them is non-zero if and only if C1 V1 plus C2 V2 equals to 0, then the set is linearly dependent. say this is a part of linear combination, you find this one. This whole expression. This is the member of span. That means if this is equals to 0 in such a way that at least one scalar is non-zero, at least one scalar, maybe 2, maybe 3, up to n, but at least one scalar is non-zero, then this is called linearly dependent. So here you see the example, you can verify this. I write this one 2, 1, 0 minus 3, 0, comma 1, and this I write minus 1 of 2 minus 3 equals to 0. See, this is C1, this is D1, C2, V2, C3, V3 equals to 0, and here you find C1 is 2, C2 is minus 3, and C3 is minus 1. This is not equals to 0. This is also not 0, this is also not 0. So if at least one of them is non-zero, then this is linearly dependent. If every scalar is equals to 0, then it will be linearly independent. Okay, so this is the situation. Linearly independent and linearly dependent, these concepts are very important, and this will play an important role to explain the structure of vector space. And M22, let V1 is 1, 1, 0, 1, V2 is 1, minus 1, 1, 0, and V3 is 2, 0, 1, 1. Determine whether the set from V2, V3 is linearly dependent. If we look at this, we find here V1 plus V2 is V3. That means V3 is 1 times of V1 plus 1 times of V2. So V3 is a linear combination of remaining two. Therefore, set V1, V2, V3 is linearly dependent sets. Okay? I'll give you one problem, so you just simplify this. In P2, determine the set 1 plus x square, 1 minus x plus 3x square 1 plus 3x minus x square is a linear dependent. Okay. Check for Li object L. 1 plus x plus x square, 1 plus x square in P. Okay. 1 2 4, 2 1 3, 4 minus 1 in R. Okay. So these are two questions. You just try what is going on. Thank you very much. Jai Hind.